Okay, in this video we are going to formalize the idea of a quotient group. By the way, in Gallien's textbook, quotient group is called a factor group. Okay, in case you're wondering what the relationship is between those names, or like why there's two different names for the same thing, consider the fact that if I divide 12 by 3, I get a quotient of 4, but that also means that 4 is a factor of 12. So you can think of a quotient and a factor as being kind of the same thing. Of course, here we're going to be doing a lot more than dividing integers. We're going to be taking quotients of groups modulo normal subgroups. So here's the definition. Let G be a group and let H be a normal subgroup of G. Then the quotient group G mod H, and again that is pronounced G mod H, is the group whose elements are the left cosets of H in G and the operation, and whose binary operation is defined by AH multiplied by BH is, well, it's the set that I get by multiplying elements of those two cosets together. Okay, so that's my definition. But the first thing you should be asking yourself is, okay, fine, this operation is well defined as to what it gives me. Like if I take a coset here and a coset here, fine. The product of those is the set of all things you get by multiplying elements of this coset by elements of this coset. But the first question we should ask is, wait a minute. Is this really a left coset? Because if it's not, then this isn't really a binary operation. A binary operation on cosets should take two cosets and give me a coset of the answer. So if this thing is not a coset somehow, we're in trouble. All right, so the first thing we need to prove is that if H is normal, that thing really is a coset. So here's a lemma. Suppose G is a group and H is a normal subgroup of G, normal. Then, if A and B belong to G, any elements of G, then the product of these two cosets is equal to this specific coset, the left coset of H containing AB. And just so that we have this here, the definition we're using is that AH times BH is the set of all xy such that x belongs to AH and y belongs to BH. All right, so here's the proof. We're going to prove this using good old-fashioned set equality. All right, so here's the proof. We're going to try and write the proof over here in the right-hand column. And let's let A and B belong to G. Okay, we'll show that AH times BH is equal to ABH. Each of these sets has a definition. The set on the left is the set consisting of anything that's an element of AH times an element of BH. The set on the right consists of anything that is AB times an element of H. All right, I think we could probably prove this part relatively easily. Easier than the other part for sure. So to show that ABH is a subset of AH-BH. I think this is the part that's going to be relatively easier. Suppose that Z, I'm trying to avoid X and Y for now because I used X and Y over here, and I might want to use those symbols to represent elements of AH and BH respectively. Suppose Z equals, or Z is an element of ABH. All right, then what's the first thing we know? Then Z is equal to ABH for some H belonging to the subgroup. All right, well then, well, just a minute. Z is equal to A times BH. BH is an element of this coset here, and A, if you take that to be A times the identity, that's an element of this coset here. So, well, A equals A times 1 is an element of AH, because 1's an element of H. Remember, 1 means the identity here. And BH belongs to this coset. Okay, so Z, which is equal to A times BH, does belong to AH times BH. Okay, so that's great. So we know that at least this ABH, this coset, is a subset of this set. The question is whether this will be a subset of this. And that's the part that failed in the last video, where we talked about a group that wasn't normal, or a subgroup that wasn't normal. All right, so just summarizing what we've done so far. So now we know, now we have ABH is a subset of AHBH. Great. Okay, so now to prove the converse. Now, let Z be an element of AHBH. Okay, so using my set definition over here, remember, a good thing to do always is try using the set definition and see if that gets you some traction. So Z equals XY for some X belonging to AH and some Y belonging to BH. Okay, and I can unpack that further. I can say, so there exist H1 and H2, both in H, such that X equals AH1 and Y equals BH2. So what do we know so far? So we know Z is equal to AH1 BH2. And remember, I'm trying to show that this belongs to, let me just put this in a different color so it appears as an aspiration, not as something that we know yet. Okay. So I want this to be in ABH. Good to remind ourselves of what we're trying to do. All right, so why might that be true? I mean, I'm hoping that I can do the following thing. I'm hoping that I'll be able to move B over here somehow so that I'll have A times B times an element of H. And the thing that I have to remember is that I can't just move B past H1. I don't know that B commutes with H1. I don't know that any of this stuff commutes. However, I can do the following thing, and this is just from knowing that H is a normal subgroup. Okay, we know H1b belongs to the coset, the right coset, HB. And that we know without knowing that H is normal. That's just the definition of right coset. But because H is normal, H is a normal subgroup of G, HB equals BH. The right coset and the left coset are exactly the same. So this means that H1b belongs to BH, and thus there is some element of H. It may not be H1, but there is some, and I'm going to call it H3 belonging to H, such that H1b is equal to BH3. In other words, I can express H1b as an element of the left coset BH. B times some element of H, maybe not the same element. Okay, so let's take stock of what we know. So Z equals AH1 BH2, and now we know H1b is equivalent to BH3. Okay, now we're getting somewhere because I've got AB times this product H3H2, which belongs to H. All right, so since H is a subgroup, just because it's a subgroup, we don't even need normality for this. H3H2 is an element of H. So because I have that, Z belongs to ABH. And so we've shown AH times BH is a subset of ABH. And therefore, we've proven that ABH, that left coset, and this thing, AH times BH, those are exactly the same thing. Hooray! All right, so let's summarize here. Let me zoom out a little bit so we can see everything that we've done. Okay, so zooming out, there we go. That proof went a little bit longer than I thought. All right, so in summary, we've proven that AH-BH is equal to ABH, just that one left coset, which means that this operation I defined earlier, it actually is a well-defined binary operation on left cosets, because multiplying any two left cosets gives me something that is, here we are, a left coset. That's great. By the way, in a lot of textbooks, it's the case that that's actually just taken to be the definition of left coset multiplication in the quotient group. Like, they'll actually define AH times BH to be ABH. But then you still have to show that that's well defined. Like, you can't just go doing that and then stop there. So for us, the fact that this is well defined comes from the fact that we just multiplied two sets of elements of our group. And then what we have over here is just the product of anything here times anything here. So if we were to call these cosets by different names, and you can call a coset by many different names, like you can call this by replacing this with any element of the coset. If we called this by different names, then we would still have the same set of elements over here, because we're still taking any element of this coset times any element of this coset, and the names are immaterial to our definition. In this definition, it's a little bit different. Here, the way that you define the operation appears very much to depend on how you name these cosets. Like if I'd said this is some other, well, let's say it's the same coset, but that coset has another name, and that name is A'H. So same coset, different name. Well, now this becomes A'BH, and you have to show that A'BH is the same left coset as ABH. And that does turn out to be the case. It's not a problem as long as H is normal. But either way, there's some well-definedness that you have to prove. Okay, so now we have a group, we have elements, we have an operation. Now we need to show it's a group, like this is actually a group, not just a set with a binary operation. So we've proven that there is a binary operation. We've proven that this set is closed. Now let's just roll through the things that we need to prove in order to show this is a group. So to prove this is associative, this operation is associative. I think not too bad at this point, because if we have AH, BH, and CH, these are all left cosets in G mod H, then, well, what is all of this? AH times BH times CH, that's the same as AB, H times CH, and then that's AB, C times H. And by the way, this is true just because I showed that AH times BH really is the left coset ABH. But now I can use associativity for G to rewrite that as ABCH. And then you can probably imagine what's going to happen next. That's AH times BCH. And then that's equal to AH times BH times CH. Okay, so multiplication of cosets is associative. The identity? Well, take a minute and maybe even pause the video and think about what the identity might be. Okay, all right, I'm assuming if you're still listening, that means that you'd like to talk about it. So we claim that H, which is incidentally equal to 1H, is an identity. And that's true because if AH is an element of G mod H, an element of the factor group, then AH times 1H is equal to A1H, which is really just AH. And same argument pertains to 1H times AH. Okay, so at this point, what we're doing is we're just using the relevant properties of the group G. And we're using the fact that even though what we're operating on is cosets, the operation looks an awful lot like the operation on G. It's just filtered through these cosets. And finally, inverses. Let AH be an element of the factor group or quotient group. Then I claim A inverse H, where A inverse is just the inverse in G, that this is an inverse for AH. And this is because AH times A inverse H, well, that's just A inverse H, which is 1H. That's just the subgroup itself, and the subgroup is the identities we just showed. Same thing if we operate the other way. Again, we get 1H, and I think now we are done. Notice that there's no guarantee that the quotient group is abelian. Like if I multiply two cosets this way, like AH times BH, there's no guarantee I get the same thing if I multiply BH times AH, because the result of what I get is either AB or BA times the subgroup H. However, interesting fact, it's not necessarily the case if I have a non-abelian group. The quotient group may be non-abelian, but it doesn't have to be. It actually could end up being abelian, and we'll talk about that some more later on.